friends, we're going to talk a little bit about slope from a different perspective than what we're used to seeing. So we do know that slope is m, that's the variable that represents slope, and that's represented by the equation y2 minus y1 over x2 minus x1. Okay? And if we are looking at that on a graph, that is represented kind of by rise over run. So that would be to say that I have a point here, and maybe I have a point here, and I can call this point x1, y1, and I can call this point x2, y2. So that's what we're used to seeing from Algebra 1 when we talk about slope. But sometimes the slope isn't always going to apply. So if I had a quadratic equation, this doesn't make a straight line. So I'm going to have a different slope at different points along that quadratic. But what we can do is we can use that to approximate the slope for a given point. So say that I wanted to look at this point here. That point is going to have slope, and that's going to be the tangent line. And so I'm going to draw this tangent line that you learned about in geometry, and that's just a line that touches the parabola at one point. Okay? And what I did here is I picked 2 points that are parallel to that tangent line. So they would have the same slope because they are parallel. Okay? As we get closer and closer to that point, something interesting is going to happen. But before we get there, let's use our function notation. So we know that x is our input. So we can call this point x. So that means that instead of calling it x1, we're just going to call it x. And for our output, we're going to call our output there f of x. So we're going to use that function notation where y can be written as f of x instead. And then we're going to say that this dot here is some distance h away from our first spot. So if I take x and add it to h, I'm going to get this next second input. So here, instead of my input being x2, we're going to call our input x plus h. And that means that our output is the function of x plus h. So f of x plus h is our output at that point. So we have these 2 points that are parallel to make a red line that's parallel to the blue line or the purple line. That purple line representing the slope because it's tangent to that point that we're interested in. Now what we can do is we can move these points closer and closer together until that h becomes 0, or the distance between the points is 0. And when the distance between the points is 0, then we are at this point, which is why we can approximate the slope using this, this parallel line. So then if we take our slope equation, we can rewrite it with some substitution. Instead of y2, we can use f of x plus h. Instead of y1, we can do f of x. Instead of x2, we can do x plus h. And instead of x1, we can do x. And that's going to simplify where x and minus x cancel out. So another way of writing slope using function notation is f of x plus h minus f of x all over h. So that's a really interesting definition here where we're using complex function notation to define slope. And the reason that this is interesting is because this is part of the definition of a derivative. And literally what a derivative is the slope at a given point. So that's why these two things relate.